All right, this is section 11.1, sequences, second video. So now that we've seen an example of what a basic sequence looks like and how to notate it, let's talk about how it looks visually and how we can identify limits of sequences. So the first example we saw, part A of example 1, had the sequence n over n plus 1. So you might ask, what does this look like on a graph? So there's a couple different ways that you can visualize it. On this left, we have a number line where there's a mark that represents each of the sequence values. You can see 1, 2, 3, and 4 identified, and then of course it gets closer and closer to 1. And then over here on the right, we have something that we're probably more comfortable with. We have a Cartesian coordinate system where the x-axis is n, which is our counter, our subscript, and then the y-axis is the sequence value itself. One thing that's kind of important to note is that when you see all these dots, your mind intuitively turns this into a graph and connects the dots. But sequences only have values where the x value or the n value is an integer. So technically there are no values between n equals 1 and n equals 2, even though your brain connects the dots here. But you can see a pattern that the sequence values are getting closer and closer and closer to 1. Of course, for example, when n is 100, the sequence value is 100 over 101. So as n gets larger, the values of this sequence gets closer and closer to 1 is what we can see here. So here we're just re-mentioning that technically there's nothing in between the points. It's isolated points, 1, 2, 3, 4, 5, 6, 7, and on. And like we discussed, it looks like the values of this sequence are getting closer and closer to 1 as n becomes large. And what they show here is if you take the difference between 1, which is our theoretical limit that we haven't proven yet, and the values of the sequence itself, meaning what's the difference between 1 and the sequence, how close does it get? When you do that subtraction, you get 1 over n plus 1. And I think you guys can probably remember from when we were doing limits at the beginning of the course, or the beginning of Calculus 1, that 1 over n plus 1 is absolutely going to go to 0. Because as n goes towards infinity, we would have 1 over a huge value, which gets closer and closer to 0. So what this is saying is, yes, these values do approach 1 because the difference between these values and 1 gets incredibly small. And we can indicate that limit exactly like you think you should. The limit of the values of that sequence, n over n plus 1, as n goes to infinity is 1. So basically all of the same rules apply when you're taking the limit of a sequence as when you're taking the limit of any other function. So the notation is the same. We have the limit as n approaches infinity of a sub n equals big L, capital L, which means the terms of this sequence a to the n approach L as n goes towards infinity. Okay, so again, it's almost the exact same idea as when you're taking the limit of a function. And there's a couple of different ways we can write that. We can say the limit of a to the n equals L, or we can say an approaches L as n approaches infinity. And remember from back when we first learned about sequences, or I'm sorry, limits, that what this means is as n approaches infinity, as that difference becomes very small, the difference between a to the n and L also becomes very small. If you'll remember, we used, I think, epsilon and delta to indicate that when we were doing definitions of limits. Now, if this limit exists, if L is a real number, then we say the sequence converges. And if it does not, then we say the sequence diverges. You've already heard this language. Where have we heard this language? I think infinite integrals. I'm sorry, I couldn't think of the right word. We've already had this idea of something converging or diverging. Before we had the idea that if the integral existed, then it converged. And if the integral didn't exist or was infinity, you would say it diverged. And that same exact idea is true here. If you can find that the limit of an is a real number, like in the previous example, it was 1, that means that sequence converges. But if you end up getting infinity or can't find that it converges, then you would say the opposite, it diverges. And here is an example of two sequences that have the same exact limit to show you that you don't have to simply approach a value like in the first example. Let me go back. Here's our first graph, and you can see the values get closer and closer and closer to 1 as n approaches infinity. But it doesn't have to have that same pattern, and that's what these two graphs are showing. In this first graph, the values shoot up way higher than L, but then come back down and start to get closer and closer. And then in this last graph, you can see that it's bouncing around kind of like a trig function, but with each cycle, the values get closer and closer to L as n gets large. So several different sequences could have the same limit, but have a different type of behavior if you were to graph them. So just sort of an FYI. Okay, so back to the idea that the way we write sequences can look sort of like a function. The difference being that the values of a sequence don't exist in between the integers, whereas a function can exist at any number, any real number, x. But the nice thing about that is a lot of the same theorems and the same ideas apply because they are so similar. So for example, if you have a function, f of x, and the values of f of x, where x is an integer, dictate a sequence, an, then you know the limits are going to be the same. So what you see on this graph, the red, or sorry, it's not red, I guess, the pink line is the function f of x, but all the little dots on that line are a sequence, an. Well, if you know that this function has a limit, then the sequence would also have the same limit. So as a sort of example, you'll remember that we've looked at the limit of 1 over x and 1 over x to some value many, many times. As x gets large, 1 over x goes towards 0. And if you raise x to some integer or some positive value, then it gets, the whole value gets smaller even quicker because the denominator is getting bigger even quicker. So we already knew this value, and we've been taking it for granted for several weeks now when we have worked on limits. Then we can switch this over to limit notation and have the limit as n goes to infinity of 1 over n to the r equals 0 if r is greater than 0. So all we really did here was take a known limit and sort of change the notation to make it look more like sequence notation so that we can use the same idea. So what this says is, as n approaches infinity, as long as r is positive, 1 over that value is 0. The limit of that value is 0. Okay, now if a to the n, I keep saying a to the n, I mean a sub n, I apologize for that. If a sub n becomes large, as n becomes large, we use the notation, the limit of a sub n equals infinity. Literally meaning if a sub n continues to grow and grow and grow and grow, then we would say the limit of that sequence is infinity. What does that mean? Same exact definition from when we first defined infinite limits several weeks ago. So the limit of a sub n is infinity means for every positive value m, there is an integer capital N such that you can find a sequence, one of the sequence values that meets that value. So no matter how high you go in the y direction, you can always find an x value that will correspond with that y value. Again, if you go back and look at the original definition of infinite limits, this is identical. But ultimately, if the limit of a sub n equals infinity, definitely that means that that sequence diverges, or that sequence is divergent. Okay, limit laws. These are all the limit laws from functions. Guess what? They are exactly the same for sequences. So we're listing them here, but we're not going over them again because you already take these for granted every day when you work with derivatives and integrals. And then a special fact about sequences, which is not true for functions, is if you know that the limit of the absolute value of your sequence is 0, then the limit of the regular sequence without the absolute value is also 0. And then another function says if you apply a continuous function to the terms of a sequence that's convergent, then that result is also convergent. So if you know that the limit of your sequence is L, meaning it's a convergent sequence, and you have a function f that is continuous at that value L, then if you plug all of those values into your sequence into f and take the limit, you'll get f of the limit itself. So if you look at the difference between this bottom line and the first part, they've simply put an f around both pieces, f of a and f of L. So that's sort of an interesting theorem. Okay, this is the end of video 2.